Good day, everybody. Hope everyone's doing well today. In this lecture, we are going to talk a little bit about fluids and soils, and particularly how fluids can flow through soils. Now, whenever we look at undesirable behavior of soil, it usually almost always involves fluids. I mean, fluids and soil together are kind of like when your two kids, or when you have a kid who's a good kid, but they have a friend that's not that good of, you know what I'm talking about. And when your kid hangs out with that one kid, then your kid always gets into trouble. And that's kind of what happens when soil gets with water and fluid. Um, and for a lot of civil engineering applications, we need the soil to control or limit in some way the behavior of the fluid. And so these two things, fluids and soils, are always going hand in hand and can be problematic and challenging to engineer. So in this lecture, we're going to learn some of the basic fundamentals that engineers need to understand about how fluids interact with soils, and particularly about in fluids. So a lot of this lecture is going to be review from a course like fluid mechanics, but those types of understandings or prior experience will be necessary to understand and engineer soil to control fluids. So really you should have as a prerequisite some experience in like a fluid mechanics course. It will really help you out with the stuff we're going to talk about. So as I mentioned, fluid flow through soil is a problem that all civil engineers need to deal with, and that we need to have methods to be able to handle. There, there are really two governing equations that civil engineers use to handle fluid flow through soils. And there's many, but the two big ones are Bernoulli's equation, and some engineers know this as the energy equation. And the second is Darcy's law. So these are the two equations that we're going to focus on in today's lecture. So let's review Bernoulli's equation and the concept of the hydraulic gradient. So if I have any amount of water at all, any body of water, really we can look at water in terms of energy. And we know that the total amount of energy that a water has, we can call that its total head, and that's equal to H. Then we know that the total head, or the total energy in water, is a summation of the portion of energy due to pressure, due to the elevation or height of the water, and due to the velocity of the water, if it's flowing or moving at all. So all power, all energy that's contained in any fluid has got to come from pressure, its elevation, or its velocity. That's what Bernoulli's equation is giving us. And by the way, it's this equation that governs, interestingly enough, the flight of airplanes. I mean, because of this equation, we have airplane flight. It's pretty remarkable. So in soils, we're going to simplify this equation down a little bit. If you focus on the velocity head for a moment, you'll see that in soil, fluid flows around soil particles very, very slowly. And it has to because there's so little pore space. And so if we were talking like maybe 2 feet per minute of flow, that would be pretty screaming fast in soil. But take this 2 feet per minute and plug it into this equation, and if you were to calculate it out, what you'd get is about 1.7 times 10 to the minus fifth feet of energy, which is, for all intents and purposes, zero. So if that's the case, then for geotechnical applications, we can make this whole term just go to zero and ignore it. And if that's the case, then we can simplify this Bernoulli's equation down to this little equation down here. where we're going to call H now the piezometric head, um, like a piezometer, which is a tube that you're going to stick in the ground and just see how high the water rises inside of it. It's not the same thing as total head that we talked about up above because we are neglecting the velocity head, but they're approximately the same in soil. Okay, so we're going to study this figure for a little bit because it's important that we understand some of these concepts of hydraulics and fluids and energy. Let's say that I have a pipe and my pipe is filled with soil. Now, I'm just going to cut out a section of this pipe, and that's what you see on your screen right now is my section of pipe, and we're looking at the cross section of that section. Okay, so let's say right here I take a drill, and that's my attempt to draw a drill. So now I'm going to drill a hole in my pipe, and I'm going to stick this tube down in there, and I'm going to stick it all the way down to point A, right in the middle of my soil. And if I leave it there for long enough, what's going to happen is that water is going to start rising up, rising up, rising up into the pipe until it eventually hits some level and it's going to stop. Okay? Now, let's go back to Bernoulli's equation. How can we relate that level of energy in that water to total head? If I draw some line, any line, and I call that my datum. The definition of a datum is a reference line, but it's constant. It cannot move. You can't shift it. Once you define your datum, it is what it is. The piezometric head, or we'll assume and we'll call it the total head, is by definition the height from the datum to the top of the water in my piezometer. So this guy right here. That is my total head. Okay, now you're going to see that the total head is the summation of the pressure head, which is just the height of my water in my piezometer down to my point of interest. So this guy right here is my pressure head. So think of pressure head as just the weight of the water itself. That's really what pressure head is coming from. And then the elevation head is just the distance from my defined datum to my point of interest, which in this case is point A. So if I sum the elevation head with the pressure head, I get total head. Okay, so that's how Bernoulli's equation works with a given piezometer. So in review, total head is the height that the water level rises up in a piezometer relative to some defined datum. The pressure head is the depth from the top of the water in the piezometer down to my point of interest, in this case point A. And the elevation head is the vertical distance from my datum up to my point of interest. And the total head is the summation of the pressure head and the elevation head. Okay, so hopefully we've got some of those concepts down. Now imagine I'm going to take my drill a little bit further down the pipe, and I'm going to drill another hole, and then I stick another tube down all the way to the middle of the soil, and I'm going to call that point B. And like before, water is going to start rising up into my tube. It's going to rise, rise, rise until eventually it gets to a level and it's going to stop rising. Now here's the interesting thing. I can do the same thing, okay? The total height from the water surface in my piezometer down to my datum, and remember, it has to be the same datum. That's the rule. So the height from my water down to my datum, that again is total energy. And the depth from the top of the water down to my point of interest, that is my pressure head. And the height from my datum up to my point of interest, that's my elevation head. Okay, so if I were to compare now the energy of water from point A as the water travels to point B, what do we notice? What do we see? Well, the water rises higher in the piezometer at point A, which means that it has more energy. But it doesn't rise as high at point B. Why? Why is that? Well, because we had head loss. That could be due to friction, is the most likely cause, okay? The water has to work its way around the soil particles, and in doing so, it loses energy. How much energy? Well, it's just the difference in the total heads. The difference in the total heads between point A and point B is the total amount of head loss or energy lost in the flow of the seepage of the fluid through the soil. Now this is significant because as engineers we often want to control the behavior of water by using soil, which means we use soil kind of like an energy dissipator. We use soil to remove energy from the water so that we can get the water to behave in a way that we want it to, so it doesn't flood our cities, doesn't run amok, but it goes exactly where we want it to. Now, let's play with this just a little bit. I do have a typo here. I want to apologize. I was going to correct that right now. Okay. If I wanted to compute the change in head, or my head loss, it's simply the total head at point A minus the total head at point B. Now if I substitute in the Bernoulli equations for my total heads, also taking the piezometric assumption where the velocity head we assume is equal to 0, then I have these two equations. Again, I'm correcting the typo in my math. That should be a plus right there. All right, that's how I get my change in head. Now, what if I divided that head loss, or that change in head, by the distance that the soil travels? Or not the soil, I'm sorry, distance that the water travels. It's not letting me write right there on the screen. Yes, I love technology, but not as much as you see. There we go. All right, bonus points down in the comments if you can tell me where that song came from. Now, if I take that distance that the water travels between point A to point B, the shortest distance, I'm going to call that L. And if I divide my head loss by that shortest distance, I get a unitless ratio that I'm going to call I, and that I is what we call the hydraulic gradient. It is the total head loss per length of seepage of the water. And it is a unitless number. It has no units because head is in units of length and length is in units of length, so the units cancel themselves out. So we use hydraulic gradient as an indicator of how fast the soil is having to dissipate the energy of the water. And if we introduce too much energy into the soil won't be capable of dissipating it, and the soil will be picked up and carried away. That's what erosion is. Now, we're going to get to an interesting topic here called Darcy's Law. And to talk about Darcy's Law, I want to do just a little introduction to some things that Darcy and some other investigators saw. So Darcy did some interesting experiments where you could have two side-by-side water tanks. And the water tanks could be connected with a tube or a pipe. And we could fill that pipe with, let's get a little thicker here, soil. So the brown here represents soil. I'm an engineer, not an artist, so bear with me. Okay. Now, actually, let's switch to blue. Now, imagine filling up this side of the tank with water, okay? And the point where this side of the tank is completely full of water. And of course, that water, if we open up the valves, the bottom of the tank is going to want to seep down, and it's going to want to come into the soil. And eventually it's going to start working its way through the soil and come out the other side, and it's going to want to come up into this tank over here. Now, we're going to pause the experiment right here, because this is something interesting that Darcy saw. I'm going to draw just a datum line. Now, if I take the height from the top of the water in this tank down to my datum line, that's my total head in tank 1. And if I take the height of the water in the second tank down to the datum that I drew, datum, that is head 2. And of course, the difference in those two heads is what we call our delta H, or that's our head loss. But here's the deal. If this is a closed system, this water in tank number 1 is going to move all the way down into tank 2. And eventually this water is going to go up, and this water is going to go down. And delta H is going to get smaller and smaller and smaller until eventually it's going to equal 0. And once it equals 0, what's going to happen is it's going to equal 0 when the two water levels equal one another. Yeah, you get the idea. Okay. And so when the two water levels equal each other, then we've got 0 change in head. At which point, if I'm computing hydraulic gradient, because I know it's change in head over length, where this distance of the soil is my length, if my change in head is equal to 0, then my hydraulic gradient will also equal 0. Now here's what Darcy observed. At the beginning of the test, like this, he was measuring the velocity of the water. And he noticed that the velocity of this drawdown in tank number 1 was really fast at the beginning of the test. And the velocity of the uptake in tank 2 is really fast. But as the two water levels started to equal each other, and as the head loss started to approach 0, the velocity slowed down, and the rate of the drop in tank 1 was slower, much more significantly than it was at the beginning of the test. And so he started to plot these different occurrences relating velocity to hydraulic gradient. And this is what he saw. On this axis we have the velocity of the water dropping in the tank, and on this axis we have the hydraulic gradient between the two tanks. And he saw a linear relationship. That the higher the hydraulic gradient, the faster the discharge velocity. The lower the hydraulic gradient, the slower the discharge velocity. And when hydraulic gradient was equal to 0, guess what? The velocity was equal to 0 too. The water became stagnant and wasn't flowing anymore. So then he defined the slope of this line as K, which was named the hydraulic conductivity of the soil. This is a measure or a quantification of a soil's ability to permeate or to transport fluids through it. So now, based on this linear relationship, we know that velocity is equal to K, or the hydraulic conductivity, times I. But we also know that velocity is just equal to flow, Q, divided by the cross-sectional area of our pipe. So this is if I went and cut the pipe where the soil is in half and just flipped it on its side. This is the cross-sectional area of our pipe. So if I substitute then flow into this equation for volume, what I get is this equation right here. And this equation is, that equation right there is Darcy's law. And this is a very useful equation for so many engineering purposes and functions. A few things we need to be aware of about Darcy's law. It's only valid for laminar flow conditions, so really, really slow flowing fluids. There is no apparent lower boundary for this flow, meaning it can go all the way down to 0 and the law still holds. But the upper boundary for laminar flow is when we have a Reynolds number that is less than 10. If we get over 10 with our Reynolds number, then we no longer have laminar flow and Darcy's law does not apply. Here are a couple of typical values that you might be interested in units of centimeters per second of hydraulic conductivities for various soil types. Now, one thing that I want to talk about that is pretty interesting. Let's go back to our little whiteboard here. When Darcy was measuring velocity, what he was measuring was the rate of that the water was dropping in the tank. Okay. But here's an interesting question for you. Let's get a different color here. One because I'm colorblind, it's got to be one that I can see. Is the flow through this portion of the pipe the same as the flow through this portion of the pipe if we have steady state seepage? Well, yeah, it would have to be. The flow in has to equal flow out. Okay, well that's great. So I know then that flow is simply equal to velocity times area. All right, so flow has got to be constant in the whole system. This area, right, is the cross-sectional area where our fluid is flowing. Now, in the pipe, where I have my first orange arrow right here, the pipe is not clogged at all. It's perfectly open, and so the cross-sectional area is going to look something like this. Now, if I take a cross-sectional area in this section of the pipe, it's going to look a little bit different, right? It's going to look a little bit more like this, because there's soil in there. And the only place that the water can flow then is between the soil particles that show like they're white on the screen. And then if I go back to maybe this section over here, whoops, that's too thick. then the cross-section of that pipe is going to be wide open. So my area is changing. But if flow is constant, then that means that my velocity has to change too. So in the soil itself, because the cross-sectional area through which the water can flow is so much smaller, it's really only the void space. All this stuff that I'm coloring in, that's the effective cross-sectional area that the water can flow. Because that's so much smaller than the pipe before the soil, that means that the velocity has to increase, the velocity of the flow or the velocity of the water has to increase in order to maintain constant flow. Decrease area, increase velocity. So we can look at it in another way. So here I have another tube. I have a tank up here that empties into a lower tank down here. And soil in the middle, so the flow is going down that way. Imagine if I took all of the soil particles, all of the solid soil through which the water cannot flow, and I just pack the sides of this tube with those solid soil particles so that I just have solid soil around this pipe. So here's the cross section of it now. Think of it almost like a blocked artery in your heart or something like that. If I now take this cross section and I flip it over here and look at it, this is all solid soil around the edges, and the only place that the water can flow is through the voids, and that's right here in the middle. Okay, so we call this then the area of the voids, and this is of course the area total of the total pipe. So if we have a smaller flow area, the velocity of the water has to increase like we already discussed. We call that higher velocity V sub S, or the seepage velocity. This is the actual fluid velocity through the soil pore space. And we can compute it simply just by using this equation right here. We know flow is constant, so the discharge velocity times the total area has to equal the seepage velocity through the area of the voids. And then we do some simple algebra, solve for the seepage velocity, and what we end up getting is this relationship right here. So seepage velocity equals discharge velocity divided by the porosity of the soil. And you can recall porosity from I believe it was our second or third lecture of the semester when we talked about phase relationships. Okay, let's work through an example just to show you how this is going to work. What I have here is I have a pressurized reservoir that's pressurized to 3 pounds per square inch. At the bottom of this reservoir I have a little curvy tube of soil that is 5 feet, and then it turns and has 1 feet, and then it curves back up again, and then is another 4 feet until it exits at point C to atmospheric pressure. We know, or it's given to us, hydraulic conductivity is equal to 0.02 feet per minute for this soil in the tube. The dry density of the soil is 110 pounds per cubic foot, and the specific gravity is 2.65. It's also given that the cross-sectional area of this pipe is 1 square foot. A datum is given to us, drawn down here, from which all of our measurements are being made. Now, what we're going to do is we're going to solve for the rate of flow, Q, through this soil-filled tube. In other words, we want to use this equation to solve for the flow through the pipe. Okay, A has been given to us. That's this guy. And K has been given to us. That's this guy. But we need to solve for hydraulic gradient in order to get Q. So that's the trick to getting part A. Now part B, we need to know how long it takes for a drop of water to move through the tube. So a drop of water entering right here into the soil at point B, how long is it going to take for that drop of water to make its way around and to get to point C and get out of the tube? So what we really need to do is we want to solve for time, and that's simply going to be, let's see, the length divided by the seepage velocity. So the time is the seepage length through the pipe divided by the seepage velocity of the water. So those are the two tricks that we need to solve for this system. So pause this lecture, pull out a piece of paper, and take a few minutes and see if you can, cleverly solve these two problems. And then feel free to unpause and we'll move on and I'll show you the solutions. Okay, so hopefully you took a few minutes to try to solve this example problem on your own. Let's go ahead and look at the solution. So in order to get hydraulic gradient, that's really what I'm after. I need my change in head over the length over which that change in head occurred. So I first need the total head at point B. How am I going to get it? Well, let's compute it using our piezometric head equation. So first we need the pressure head. Now the pressure head is simply going to be the existing pressure that's in the tube that is artificial and being applied. So that's 3 psi, but we have to watch out for units. Make sure that our units are consistent. And then it's going to be simply the pressure from the depth of water down to our point of interest, which would be point B, all of course divided by the unit weight of water. So the depth of water here in our tank is simply 8 feet minus 6 feet. And we get those measured from our datum. So once we have that depth, that's 2 feet deep of water, we're going to multiply it by its unit weight of 62.4, and that's how we get our pressure from the water. That's this P right there. And then we'll divide that by the unit weight of water to get it in terms of head or units of length. Now the elevation head is simply the height from our point of interest down to the datum, or the height from the datum up to the point of interest, which in this case is 1 foot plus 5 feet, or that's where our 6 feet comes from. So now if we do the math, we get 14.9 feet of total head at point B. Okay, let's do the same thing for total head at point C right here. The pressure at point C, because it's open to atmospheric pressure, we know is 0. And the elevation head, so this is the height from our datum up to our point of interest, is 5 feet. So that one was easy. The total head at point C is just 5 feet. So now to compute the difference in head, or delta H, we just have to subtract the head at C from the head at B. And that's where we get 9.9 feet of head. 9.9 feet of head loss in the soil there, in the tube. Okay, so now we just need to that gave us the head loss. Now we need to get the length over which that head loss occurs. So that's the distance from B down to the bottom of our pipe, which is 5 feet, plus another foot to the right, plus another 4 feet up to point C. So 5 feet plus 1 feet plus 5 minus 1, which is 4 feet. And so that's going to give us 10 feet. So now we have our length. I can compute then my hydraulic gradient as the change in head divided by my length, or change in length, and that gives me a hydraulic gradient of about 1.0. So you'll recall that the hydraulic conductivity was given, cross-sectional area was given, and I just have to plug my hydraulic gradient in to this equation. This again is Darcy's law, and computing the numbers we get 0.02 cubic feet per minute. Well, I'm probably going to want mine in cubic feet per second, so I do a quick unit conversion, and there's my answer right there. Okay, part B, we have to get the time for the flow. So as we mentioned, time is going to be equal to length divided by some velocity. In this case, it's going to be the seepage velocity, because we're interested in the velocity of the water as it travels through the soil pore space. So we have to relate then seepage velocity to something that we can compute. And we can compute discharge velocity from Darcy's equation, because remember that V is equal to K times I from Darcy's law. And then we have, of course, divided by the porosity to get us to the seepage velocity. So I can do some math quickly, and this is the relationship I'm going to use for this particular problem. Well, how do we get then the discharge velocity? We're going to use the flow we computed in part A and just divide it by the cross-sectional area of our pipe. And that's how we get 0.02 feet per minute. That's our discharge velocity. Now to get our porosity, we're going to go back to a phase relationship that we had, which is this guy right here. It comes out of our textbook, our DOS textbook, equation 3.27. And we can solve it then, or manipulate it to solve for porosity. And if I plug in the numbers then that I've been given, 110 for the dry density, 2.65 for the specific gravity, and of course 62.4 pounds per cubic foot for unit weight of water, I get 0.33 for my porosity. So now I just plug porosity in right there, I plug discharge velocity in right there, and we computed the length of the soil flow, which was 10 feet. And so I just do the quick math, and there's my answer. 165 minutes for a drop of water entering the soil at point B to work its way all the way through the soil and come out at point C. All right, let's switch gears just a little bit. We're talking about hydraulic conductivities, and all of these homework problems, it's just a number that's given to you, as if we can just go to the hydraulic conductivity tree and pick a number off of it. You may be wondering, well, how do we get hydraulic conductivity? Where does it come from? And that's an excellent question. The truth is we have to measure it, or we have to assume it, or we can correlate it, one of those three things. So let's talk a little bit about measuring. So in terms of measurement, there are really two general ways that we can measure the hydraulic conductivity. The first way is using what's called a constant permeability test. All of these methods, by the way, of measuring hydraulic conductivity involve using Darcy's law and just isolating the unknown, which is the hydraulic conductivity. So in the constant head permeability test, we have an upper chamber of water that we fill with water, and we leave the sink running. And why do we leave it running? Well, because we want water to flow over the edge and keep flowing so that we maintain a constant level of head. we want the water elevation to remain constant throughout the whole test. And that water is going to run and it's going to percolate down into the soil and eventually saturate it. And it's going to go down into this lower chamber. Now this lower chamber has a roof placed upon it. It's sealed, so water can't get out. And we do that so that we can control the elevation of the water, or the total head of the water, in the lower chamber. The only place water can come out is a little spigot right there where we collect the amount of water that's coming out and we can record its volume. So as water seeps through the soil, down through the soil, it's going to force water to come out through the spigot and into our graduated flask. Flow has to remain constant. So this amount of water that's in the flask, that's the volume of water, that's Q. The time that it takes for the test to run is the time that it takes to build the water in the flask. Okay, the A is the cross-sectional area of our soil tube. And then, of course, I is the hydraulic gradient. Now, the hydraulic gradient in this instance, we remember I equals delta H over L. Okay. The change in head in this case is simply the change in elevations between the two tanks of water, which is equal to H. And the L is equal to our length, or the height, of the soil. So I, in this case, is simply going to be H over L. So if we plug this relationship in for I, we get this equation here. And then all we have to do is rearrange this equation to solve for hydraulic conductivity. And voila, that is our governing equation for using a constant head permeability test. To give you an example, let's just say that we run a test in the picture here shown on the left with a given soil, and over a period of 37 hours, or 133,200 seconds, we collect 100 milliliters of water, or 100 cubic centimeters of water, in our flask. We know from this test, let's assume that the area of our cross-sectional area of our soil is 45 centimeters squared, that from our testing apparatus, that the change in head from the upper tank to the lower tank is 25 centimeters, and that's constant. It doesn't change. And the length, or the height, of our soil in the tube is 15 centimeters. That's the distance that the water travels through the soil to get from the upper tank to the lower tank. So all we need to do is plug and chug, folks. Let's throw all those values into the equation that is given, and we have to make sure that we're using consistent units, of course. But if we do that and we punch the numbers, we're going to get 1.0 times 10 to the minus 5th centimeters per second. That is how we run a constant head permeability test. Now, running a constant head permeability test requires special equipment, and it's messy because we're running water all of the time. A quicker test that is not as messy and is a little easier to run is a falling head permeability test. Now, the falling head permeability test, we still have an upper chamber of water, and we still have, of course, the lower chamber of water. But the difference is we're not pouring water continuously into the top chamber. We're going to fill it up. We're going to run it until the soil gets completely saturated, and then we're going to start the test. When we start the test, we shut the water off, and we're going to watch how this level of water drops, 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 drops over a specified amount of time. Now, as that level of water drops, because of Darcy's law, we know that the velocity in that of the water flow is going to decrease as that head level drops. Okay. So all we need to do then is account for that change in hydraulic gradient with time. And then we can back calculate the hydraulic conductivity. So again, here's our governing equation. This is Darcy's law. But we know that flow has to remain constant. And if I have just a little element of water in this upper standpipe that is dH high times an area of A, so you can imagine then a little cylinder of water, right? That is dH high, whoops, not DD, dH high, and has a cross-sectional area of A. So that's a volume of water, okay? The flow in a given amount of time has to equal that little volume of water that went down as a function of time. So all we need to do now is rearrange this equation and do a little bit of integrating. So if we integrate time, and in this other side of the equation, we integrate head. We're going from head 1, which was the top, down to head 2, which is the bottom of our cylinder. Then if we integrate, we end up with this equation right here. Now, this equation is true. All we need to do then is manipulate the equation and solve for k. It's in terms of natural log. If we want to change natural log to log base 10 units, then we can just use this equation right here. So the difference between this falling head permeability test equation and the constant head permeability test equation is right here. There are two different head levels in the falling head permeability test. One's the total head at the beginning of the test, and the other, H2, is the total head at the end of the test after time t has passed. Okay. Here's something to think about, though. What are some of the difficulties associated with getting soil samples to the lab to test in a permeability test? Well, for instance, getting undisturbed samples is really hard, if not impossible. Well, why would we want undisturbed samples? Well, think about fluid flow through soil. It's all dependent upon the matrix of the soil particles. You change the matrix of the soil particles, you're going to change its permeability and the way that fluid flows through it. So if I disturb the soil matrix while I'm sampling it and taking it to the lab, guess what? I have a different soil. And what I'm measuring in the lab may not be representative of what exists in the field. Here's another problem. I'm only measuring a small sample. Who's to say that my sample, though, is representative of all the soil that's in the field? I'm only measuring one little point of soil in the field, if you think of it that way. I'd rather be measuring the hydraulic conductivity of all of the soil in the field. And it doesn't really account, and that this one ties into the second one. It doesn't really account for soil layering. And other things like heterogeneity or anisotropy, which we'll talk about in a little bit. So all of these things are really significant issues and problems. And how do we overcome them? Well, we can measure hydraulic conductivity in the field. We can do what's called a pump test. So in a pump test, we're going to drill a well somewhere where we're interested, and then we're going to put a pump down and we're going to start pumping water out. And as we start pumping water out, we're going to start drawing down the groundwater table. And eventually it's going to equalize out and it's not going to change anymore. But we're going to have this drawn down parabolic shape of the groundwater table. Okay? And it's going to remain that way as long as we're pumping water out of the ground at the rate that we are. So we can use this shape of this groundwater drawdown and the known flow that we're pumping out of the ground to back calculate what the hydraulic conductivity is in the actual soil in the ground. So how do we do this? Well, good guess. We're going to go ahead and just use our Darcy's law like we did before. K-I-A. Okay? K is what we're interested in. I is simply going to be the change in head, or the change in H, divided by the change in radius in our drawdown. And then the cross-sectional area is simply the cross-sectional area of the surface of our boring. So it's the area through which the water is seeping into the borehole, if you think of it that way. So that's why we have 2 pi r. R is, of course, the radius that we're interested in, times h. H is the height of the piezometric surface of the groundwater. Okay. So with that relationship, we can separate dr and dh, isolate them, and then integrate as we did earlier. The integration's a little more complex, but we can solve it, and we start working our way down through these different derivations, and we get to the point where we have this relationship here. Okay. And that really is the equation for the hydraulic conductivity from a field test, where R1 is the distance from the center of our pumping well out to a monitoring well where we're monitoring the piezometer and we're monitoring the height or the depth of the water. Okay? And R2 is same thing. It's the distance, the horizontal distance from the center of our pumping well out to a second monitoring well where we're monitoring the elevation or the piezometric head of the water. And H1 and H2 are respectively the total heads of the water in those respective monitoring wells, relative usually to a datum. In this case, the datum is the top of this impermeable layer. Okay. If we'd rather use log units, then that's fine. We can use this equation here on the right. Q, by the way, is the flow that we're pumping out of our well. So yeah, this is great. But this specific equation that I showed you here deals with what we call an unconfined aquifer. An unconfined aquifer means that the groundwater can flow into our pumping well unrestrained. There's no limitations. It can just flow in anywhere that it wants to, wherever the water is located. What if we had a situation like this, where we had an upper layer that consisted of impermeable or low permeability clay? Okay, and then we had a lower layer of high permeability sand. If you start pumping here, where is the water going to come from in your well? It's definitely going to come from this confined aquifer or this sand, because it has a much higher hydraulic conductivity than the clay does above it. And so this is what we call a confined aquifer. meaning that the groundwater is actually restricted. Even though there is water shown here in the clay, it's not really seeping into the borehole through the clay. It's seeping in through the sand because it can't seep fast enough through the clay to get into the borehole with our pump. So if this is the case, then we have to account for this confined aquifer. How do we do that? Well, we're going to use the same equation we did before, but this time H right here is the height of our confined aquifer, or the thickness of our confined aquifer. So we do the same math as we did before. We differentiate, or we integrate, and we get down to the point where we have our recommended equation here. The only difference now, again, is we have that thickness of that confined aquifer in our relationship. Okay? And as before, if we prefer to use the log equation, we can use this one here on the right instead of the natural log equation on the left. So let's show you how these equations might be used. Let's imagine that I have a pump test where I put a well right here and I start pumping water out at a rate of 1 cubic foot per second. And I let that pump for a long time, and eventually my water level draws down like this. And it stops moving. Okay? I put in 2 observation wells, well number 1 and well number 2. And I observe the water level in each of those wells. Now let's define a datum, which is going to be the bottom of my sand, right on top of impermeable rock. So that I'm going to use that as my datum for computing my total heads. So what I want to do is I want to find the hydraulic conductivity of the aquifer, and I want to compute the radius away from the well at which, if I were to install a new observation well, the water would be 12 feet below the ground surface. So I'm interested in where in the world would it need to be that my depth from the ground surface to the water is 12 feet. That's what I want to find. All right, let's get to it. So the first question I need to ask, of course, is this a confined aquifer or an unconfined aquifer? Now remember, a confined aquifer exists only if the water is restricted to coming into my pumping well because I have some capping clay layer or something that's preventing the water from coming into the well however it would like. In this particular instance, I just have uniform sand as my upper layer, and the water is not restricted whatsoever from coming into my pump well. So as a result, if you said unconfined aquifer, you are correct. This is an unconfined aquifer. Okay? So all we need to do to get part A is just plug and chug. We're going to use the relationship given to us that we computed on the earlier slide, and we're just going to compute the hydraulic conductivity. We have to get, of course, our heads, which are just the height of the water inside the piezometers relative to our datum. So here in monitoring well number 1, the height from the datum up to the water surface is 36.92. And that's because that's just 50 feet minus the 13.08 feet. Over here, this is 50 feet minus 10 feet, so this is where I get that 40 feet of total head in the second monitoring well. The radius from my pumping well to the first monitoring well is 40 feet, and the radius from my pumping well to my second well is 80 feet. So let's just plug those numbers in, right? Radius 1 is 40 feet. Radius 2 is 80 feet. Head in well number 1 is 36.92 feet. Head in well number 2 is 40 feet. So I just crunch those numbers and I directly compute a K of 9.3 times 10 to the minus 4th feet per second. Great. Okay, so if I want to now solve the radius at which the water will be 12 feet below the ground surface, I just have to use this equation. The only difference is I now know K. My only unknown is R2. I know H2 has got to be 50 feet minus 12 feet, which is going to be, 38 feet. So I just need to rearrange this equation to solve for R2. Let's go ahead and do that. So again, here's, or I guess R1 or H1, whichever one we want. So the head that we're interested in is 50 minus 12. That's 38 feet. I just need to find the radius that's associated with that. So if I rearrange my equation and isolate that radius, I get this equation right here. And then I'm just going to plug in all the numbers that I know, and I'm going to solve for that radius. And I get 50.7 feet away from the pump well. If I were to put an observation well down, the water would be 12 feet below the ground surface. Okay, so this is pretty powerful stuff because we can now use these drawdown equations to estimate how far down we can safely excavate, for instance, for a construction project if we were pumping the groundwater down. Because obviously if you're doing an excavation and constructing on a site, you don't want to be working in open water. So we need to draw that water down and give those construction workers, a dry place to work. Okay, I want to spend just a little bit of time, we're almost finished, I want to spend a little bit of time talking about the differences between conductivities in two different points. So imagine I have soil. Okay, I have lots of soil here, and I have two unique points, point number 1 and point number 2. How can I describe the permeability of this soil as a whole? Well, I might describe it as homogeneous. If it's homogeneous, what that means is that the permeability in the x direction at point 1 is equal to the permeability in the x direction at point 2. And the vertical conductivity at point 1 is the same as the vertical conductivity at point 2. And here's the interesting thing, though. It does not necessarily mean that the horizontal conductivity at point 1 is equal to the the vertical conductivity at point 1. All it means is the horizontals are the equal and the verticals are equal. So in other words, we can just say we have the same material between point 1 and point 2. Now what if I describe the material as isotropic? Isotropic means that the horizontal conductivity at point 1 is assumed to be the same as the vertical conductivity at point 1. However, it does not mean that the horizontal or conductivity at 1 is equal to the horizontal conductivity at point 2. In other words, it could mean that maybe there's a difference between the conductivity over here at point 1 and the conductivity over here with point 2. We can summarize that by saying it's the same permeability in X and Y at each point, but they're not necessarily the same material between point 1 and point 2. If we call the material anisotropic, that's the opposite of isotropic. What we're saying is that the horizontal conductivity is not equal to the vertical conductivity at any point in the soil. So it has a different permeability or different conductivity in the X and Y directions. and that there could be, like we said before, different materials between point 1 and point 2. Now, if we call the material heterogeneous, what we're basically saying is that the horizontal conductivity at point 1 is not equal to the horizontal conductivity at point 2, and the same for the vertical conductivities. We're basically saying that there is definitely a difference in material between point 1 and point 2. They're two different materials. So we'll often hear geotechnical engineers use these descriptors. Anisotropic, isotropic, heterogeneous, homogeneous. We need to understand what they mean. So I challenge you to, practice a little bit with these terms and quiz yourself to see if you can understand what they mean. The last thing that we want to talk about in this lecture is the idea of equivalent permeability when we're dealing with layered soil systems. That's really what we're talking about. Everything that we dealt with up to this point has been a uniform soil system with just one soil in it. But what happens if we have layered systems? We always have layered systems in the real world. Systems, for instance, where you have a thickness of sand and maybe some clay, then maybe some gravel. Now, what if we had flow simultaneously through these three different layers, but the flow was in parallel? If you recall maybe from your training in electricity or electronics, when we have flow in parallel, it means that it's flowing through multiple circuits simultaneously and then coming out on the other end. So similarly, we're flowing through multiple layers of soil at the same time, and it's just coming out the other end. If soil is layered horizontally, then this means we have horizontal flow of water. If we want to compute the equivalent horizontal hydraulic conductivity of this soil, then all we have to do is basically take a weighted average. And we get this equation here on the right, where we just take the horizontal conductivity for each soil layer multiplied by its respective thickness, and we sum all of those up, and we divide that summation by the summation of the total thicknesses of our system. So for an example up here, what I have here for my thickness of soil layer 1 of this first sand, it's 10 feet thick. And it has a conductivity of 10 to the minus 3 centimeters per second squared. My second layer is clay that's 2 feet thick, and it has a conductivity of 10 to the minus 7 centimeters per second. My third layer is 8 feet thick, and it has a conductivity of 10 to the minus 5 centimeters per second. So I multiply the conductivities by their respective thicknesses, and I sum them up. And then I sum and divide the total thicknesses of my layers, which of course are 10, 2, and 8 feet. If I do that, I get an effective hydraulic conductivity, or an equivalent hydraulic conductivity for my system of 5 times 10 to the minus 4 centimeters per second. Now wait a second. I have a 10 to the minus 7th layer right there. That's crazy. Why is this so high? Well, it's because when I have flow through soils in parallel, the high conductivity are always going to govern. My equivalent conductivity is going to be pretty close to whatever my highest hydraulic conductivity is in my system. And all that's saying is the water's wanting to go from left to right. Where's it going to go? Well, it's going to travel mostly through that sand layer, and a little bit through the gravel layer, and hardly any is going to travel through the clay. A little bit, but hardly any. So that's what we're talking about in parallel. Now what if we had vertical flow through the same layered system, but this time, like in electronics, instead of going through all the circuits simultaneously, we're going to go through one at a time until we get through the ends and we're done. Okay? So in this case, we have to do not just a simple weighted average, but this is more like a harmonic mean that we have to compute. And we're going to use this equation right here, which we can write mathematically as this. So let's solve the same example problem we had before. We're going to sum up our thicknesses, which are 10, 2, and 8 feet. And so that's where this 10, 2, and 8 come from. And then we're going to divide that summation by these different ratios. The thickness of layer 1, which is 10 feet, divided by the vertical conductivity, which we're just going to use the same numbers for this example. Thus, we would assume this soil is isotropic because we're assuming that the horizontal conductivity is the same as the vertical conductivity. So for the first layer, it's 10 to the minus 3, and that's where I get that. So for the second layer, H2, that's 2 feet. And the vertical conductivity is 10 to the minus 7th. And for the third layer, I have 8 feet thick divided by 10 to the minus 5th for its vertical hydraulic conductivity. If I solve that equation, I get 9.6 times 10 to the minus 7th centimeters per second. Now, isn't this interesting? Look at the vertical conductivity. 10 to the minus 7th. You recall that in parallel, it was 10 to the minus 4th. So when we have series in parallel, like I said before, the layer with the highest conductivity governs. But when we have soils in series, this clay layer right here, that bad boy is slowing the whole system down. And because flow in has to equal flow out, everything is flowing at the same rate as it is through that clay layer. Maybe just a little bit faster, but not much. So as a result then, our equivalent conductivity in the vertical direction is governed, let's see, for soils in series, it's governed by soil with the lowest conductivity. So it's the opposite of soils in parallel. And just so you're aware, and in case you're interested, when we perform pump tests in the field, these are the types of equivalent hydraulic conductivities that we're actually measuring because the soil in the field is in layers. And so we may be measuring a mixture between the horizontal and the vertical conductivities, or kind of like an average conductivity for the whole soil. So anyway, if you have any questions, I would be happy to answer them for you. Feel free to shoot me an email or write a comment in this video. I appreciate your attention. I know that this video is a little longer than the others, but there's a lot of material to cover, and I want to make sure that you understand them. So thank you for your time, and have a wonderful day.